Good morning, everyone. I hope you can all hear me okay. Thanks for coming along to this webinar, and the topic of this webinar is lead in drinking water. And obviously this is a particularly topical issue in New Zealand, what with some of the activity that's been happening down in Dunedin recently. So we're really fortunate this morning to have a couple of leading experts from Stantec in Canada on water quality who have assisted with some of the issues down in Dunedin recently. And we're also lucky enough to have Dunedin City Council represented. So we're looking forward to hearing some of their experiences. Before I introduce the speakers and we get going, we'll just give a couple of minutes for additional attendees to join. And while we do that, I'll introduce myself. My name is David Hogg. I am Stantec's General Manager for our water business in New Zealand. And there's a couple of little housekeeping issues that I just want to run through. Whilst this is a live webinar, there is about a 1 minute delay from what I'm saying and what you're hearing. So that means that all questions that we have, can they please be typed into the chat, the question function, and you'll find that little link at the top of the screen. It's two little speech bubbles with a question mark. If you click on that, that brings up the chat function. And so any questions at any time, please type those in, and they will obviously queue up at our end and we can work through those at the end of the presentation. And those questions can either be anonymous or you can put your name in there, but regardless of that, they won't be seen by the group, they'll just be seen by us here at this end. Okay, so excellent. Let me introduce, I see we've got about 20 or 30 attendees now, so that's great. Might start by introducing our speakers today. Our first speaker is Laith Furatian, and Laith is a water specialist practicing in the areas of drinking water production and distribution, with a focus on water quality, public health and risk management. His recent work includes long-term water master planning, guidelines for distribution system operation and maintenance, and water quality investigations. He has worked with several of our New Zealand clients, and Laith is an active member of several technical committees relating to disinfection, aesthetics, distribution system operation and maintenance, and water quality. He recently served on the BCWWA lead task force formed to better support utility members in response to revision of the Health Canada guideline for lead in drinking water. Laith is based in our Vancouver office. Our second presenter this morning is Simon Horsley, and Simon is our drinking water quality lead for Canada and US, with over 17 years experience working in both the municipal and consulting industries in process chemistry and water quality, including work with some of our New Zealand clients. His areas of specialty include drinking water treatment process design, process optimization, distribution system water quality modeling and analysis, corrosion control, disinfection byproducts management, distribution system operational management, and delivery of technical training. Bit of a mouthful there. And finally, but not least, we have Tom Dyer, who won't need too much introduction to many of us on the call, but Tom is Dunedin City Council's Three Waters Manager. And obviously we're all aware of some of the challenges that Tom has been facing recently over the past 3 to 4 months. And appreciate, Tom, you're probably not going to share everything that you are working through at the moment, but we will welcome the opportunity to have a conversation around what you are able to share. And so thank you for your time. So we're about 4 minutes in. I think it's probably enough from me. And Laith, I might pass over to you. And so the floor is yours, Laith.
Thank you, Dave. Thanks for the opportunity to share with you today. You know, I've heard people tell me, both in Western Canada and in New Zealand, that plumbo solvency in drinking water is not a problem because lead service lines effectively do not exist or are no longer currently in service. And while that may be true, and that's one of the benefits in Canada of being in a country that developed from east to west, we don't have the same level, we don't have the same issue in Eastern Canada. There's a lot of evidence to show that lead exposure can be significant from sources other than lead service lines. So the absence of lead service lines doesn't mean that the issue is does not have merit. Before I begin, though, I just want to emphasize that while lead in drinking water is a subject that merits serious consideration, the greatest hazards to drinking water safety are waterborne microbial pathogens, which pose an acute risk, whereby even a single exposure can have devastating adverse health effects, while harmful effects from lead exposure in drinking water involve a sustained exposure over an extended time. That's a very important distinction. So high exposures to lead can result in acute toxicity effects in humans. That's well established. But chronic exposures at low levels are also associated with a wide range of potential adverse physiological effects in humans, including cardiovascular, renal, reproductive effects, the most important of which are those related to adverse neurodevelopmental effects in infants and young children, potentially having lifelong impacts. And if there is, so there's a doctrine that if there is something that you can do to reduce lead exposure to children in particular, it should be done. Now, a few decades ago, lead exposure differed significantly from today. Lead was an ingredient in petrol, in paint. It was used in solders in food cans at one time, and was widely used in water distribution systems as an expensive but nevertheless convenient material for many applications, lead service lines being one of them. In many places, drinking water as a source was actually a relatively minor contributor to overall lead exposure. The soil contaminated by old lead paint chips rather, is still a legacy source of concern in some places. So as lead in various applications was eliminated, the exposure to lead overall has declined significantly, and this is revealed in records of blood lead levels in the population. Blood lead levels are an established metric for measuring exposure to lead with half-life of about 40 days. Today, average blood lead levels in the population in North America are generally a fraction, sometimes about 10% of what they were in the 1970s. So there has been some significant improvements, and there are some unexpected side effects of this. One of the impacts that lower lead levels have had is to reveal adverse physiological effects that were not as easily observed under past conditions. The measurement of adverse neurodevelopmental impacts in children is typically measured through IQ tests. And this has revealed a much stronger correlation at lower lead levels than at higher lead levels. In other words, blood lead level reductions from 20 to 15 micrograms per liter may not have actually resulted in a measurable difference in improvements. Maybe 10 to 8 micrograms per liter might have been a minor difference, but reductions from 5 to 4 micrograms per liter show a strong correlation with improved outcomes. And furthermore, studies attempting to establish a threshold for this effect below which no further improvements in outcomes can be observed, sort of a no observable adverse effect level, have failed to find such a threshold. And so it's considered a no threshold effect. And the common phrase is that there is no safe level of lead. In 2019, based on evidence gathered in this area, Health Canada reduced the maximum acceptable concentration of lead in drinking water from 10 micrograms per liter, which is the current MAV in New Zealand and the provisional guideline of the WHO, to 5 micrograms per liter. But this was not done, I want to emphasize, this was not done on a health basis, but on a feasibility basis. This was a feasibility of achievement using best available practices. The current, the recommendation actually, it goes further to say that lead exposure should be reduced to, quote, as low as reasonably achievable, or ALARA. So today in many places, drinking water has effectively become the main source of lead exposure, although significantly reduced from past levels. And it's important to know what these could be. So firstly, lead can occur in distribution systems even in the absence of frank lead service lines, such as in this image here, this a connection from to have been used as a connection between the water main and the service line, which could have been made of galvanized steel or something else, via a lead tailpiece or a gooseneck or a pigtail. It has various names. And these were once used due to their convenient properties, mostly ductility, and reduced risk of pulling on the ferrule connecting to the main and causing a leakage or a break point at the main. Once the backfill and compaction occurred. Other sources include components on the premise plumbing or building plumbing side or the private side. And this has always raised the issue of jurisdiction, since often the water supplier's responsibility for water quality officially ends at the point of supply. However, the distribution system physically includes the premise plumbing or building plumbing systems, and the chemistry of the water supplied, in particular its tendency to corrode metals, is important. So there's a duty to ensure, one could argue, that water supplied is sufficiently non-corrosive. And this issue involving the composition of the water supplied and the composition of the receiving plumbing system is often described as a shared responsibility. So sources of lead can include, currently, lead solders. These were once widely used at least in North America until the 1990s, and they've been replaced by lead-free solders for copper piping. However, you can still buy lead solder, because if you're a plumber and you're working on jobs other than potable systems, it's perfectly acceptable to be used in drainage applications, sanitary sewers applications, etc. And so I've heard utility managers tell me, well, I've seen lead solder in a plumber's toolkit. And yes, it will be there. Whether or not they use it or they're aware of the rules around its use is another question. But more so, though, is the widely used brass and bronze parts. These are common. These are common, and historically, lead was added to improve metallurgical or material properties such as machinability. Up until about 2012 in North America, the definition of lead-free brass and bronze was that it should be no more than 8% lead by weight. And after about the period 2012 to 2014, depending where you are, the definition was revised such that the wetted surface, or the portion of the part that was in contact with water, could be no more than 0.25% lead by weight. Now, such parts are commonly found as pipes and fittings, such as valves, meters, backflow preventers, and in one water supply in Western Canada, housing stock built after 2000. So they had divided the system into pre-1975, 1975 to 2000, and post-2000 housing stock, and conducted a lead surveillance program, which is ongoing. And it was found there was no difference in housing stock post 2000 in terms of lead levels. About 8% of sites sampled exceeded the Health Canada's revised guideline of 5 micrograms per liter. So brass parts are suspected as the source, and the co-occurrence of elevated levels of zinc supports this hypothesis. So NSF International has developed 2 applicable standards for materials in contact with potable water. There's NSF 61, which relates to the leachability of materials in contact with water and their resulting toxicity, and NSF 372, which specifically addresses the definition of lead-free. So parts that are used for potable supplies in North America, at the very least, must be NSF 61 or 370 and 372 compliant. But of course, there's a lot of plumbing systems out there that predate these standards, and therefore would have potentially materials that have the old value of up to 8% or even older values that predate that. I want to point. I've personally come across lead in municipal systems in surprising places, like the caulking in hydrants, which in New Zealand a different style of hydrant is typically used. But I mean, the word plumber comes from the Roman word for lead, and lead until now is still a very common material in some niche applications, but once it was widespread, and in particular in connections as a caulking with asbestos in between cast iron pipes. Now, after many decades of use, the extent to which that caulking, which should not be in contact with potable water, remains outside of the pipe is probably in general unknown. Now, one consideration in the setting of a MAV, or a limit for water quality parameters, is the ability to routinely measure and quantify that parameter. There's no benefit in setting the level so low that it can't be verified. Now, there are a few ways of measuring lead. There are a few standard methods that are accepted. The method of choice is typically ICP-MS, or inductively coupled plasma mass spectrometry, which involves quite a large instrument and a specialist to operate, but has the lowest minimum detection limit available, and is able to measure actually simultaneously a suite of metals in a sample. In general, the practical limit of detection is on the order of 1 microgram per liter or less. Depending on where you are, there may be differences in opinion on what the practical limit of detection is, but in Canada, it's deemed to be slightly below 1 microgram per liter, using the available analytical instrumentation. Now, it's also important that sample preparation be adequately addressed. There needs to be a digestion period for samples, usually involving trace metals grade nitric acid at a sufficient concentration for a sufficient time in order to capture both the soluble and the particulate lead, which are both products of the corrosion and dissolution of lead-bearing materials. But the methods such as ICP-MS will only pick up the soluble portion. So we have to convert the particulate, which can be the overwhelming majority of the sample's lead content, into a soluble one before analysis. Now, having said that, I'm going to pass it along to Simon Horsley to discuss monitoring and other matters.
Thank you, Laith. So I'm going to spend about the next 15 minutes or so talking about a number of things. I'm going to talk a little bit about lead monitoring and considerations for that. I'm going to talk about if that sampling reveals some elevated lead, how do we go about dealing with that? How do we deal with that at a system-wide water treatment level? I'll talk about the two main mechanisms, pH passivation and phosphates. And then I'm also going to talk a little bit about sort of localized corrective actions that can be undertaken by homeowners and by the utility and how those play into that picture. So if looking first of all at the monitoring side, a couple of questions to think about. First of all, why go out and start sampling for lead? Well, as Laith has just summarized, we need to sample in order to understand if the drinking water reliably and consistently has elevated lead, and by elevated we might define that as greater than the MAV of 10 micrograms per litre. Lead service lines are not the only issue. When I started out in the industry in Scotland, the lead level had not long changed from 50 micrograms per litre. It had come down to 25, and of course now being in Canada we've seen that come down to 10, and we're now seeing Health Canada look at 5. So as the levels have come down, perhaps some time ago, lead service lines were really the most likely way in which we are going to see an exceedance of, say, greater than 50. Now, as Laith noted, it's important to have low levels of lead. The research has told us that we need to try and get lead levels as low as possible. And so now homes that do not have lead service line inventory, but have other contributors, other lead-bearing fixtures like brass, and we're still seeing those types of homes, those types of communities give us lead levels greater than what we'd like to have in our drinking water. So the only way we can reliably know whether a community has elevated drinking water is to go out and sample. So I should say, in these conversations and some of the conversations we'll have in the next few slides, there's a lot to say, and I could comfortably speak for a lot longer on each individual slide. So what I would say is the intent of this is really to give a fairly high level overview, and if there's any specific areas of interest, I'd be very happy to discuss those in the Q&A. But if you do see me breeze over a subject that you might have a great deal of interest in, that's the reason why, and be comfortable to raise that in the Q&A and we can talk about it. So where do we begin? Where do we start to go out and sample? This is an evolving question. The US EPA has just brought out the much anticipated revisions to the lead and copper rule, and there's a good deal of focus on where to sample. Broadly speaking, we could summarize that as being to figure out the locations in a given community, look at the general buckets of housing stock in that community in terms of age in particular, and prioritize whatever older housing stock is there, and effectively go out and sample at all those different representative housing stock groups and see how the lead levels start to come back. That can often tell us a lot about what sort of components were being used when that housing was constructed. The question of how one should sample, there are whole sections and conferences devoted to this type of subject, so I'll really breeze over this one. But effectively, we're trying to normalize the conditions. Lead is a bit different from many of the other parameters that we collect for in distribution systems because it's quite sensitive to the method of sampling, and there are different methods of sampling for different purposes. But in general, the goal is we are trying to standardize conditions when we sample, particularly with respect to stagnation. That is to say, since the plumbing on that home and the service line was last completely flushed out, how long has the water sat within that line? There are various methodologies to try and standardize that. The longer the water sits there, the longer, the more lead can come into the water. Also, the litre number. Some samples call for the first litre after stagnation time, some for the second litre, and the new regulations in the US, for example, in some cases call for the fifth litre. So there's different reasons to look for these. If you take away nothing else from this section, I would just say it's time well spent to go and look into the different ways in which lead samples can be collected and understand why samples are collected different ways. We do want to capture particulate lead. Sometimes if we turn a tap on quite quickly and we cause a high velocity, a scouring velocity, we can scour and entrain small particulates from the wall, and we can get a sudden spike in lead as a result when that particulate is then dissolved in nitric acid, and it becomes a part of our total lead measurement. So sometimes we see spikes in lead results associated with particulate. We do want to capture that particulate because that is part of the profile that residents are seeing when they drink. And so there are some different things to think about there, not having aerators, using wide mouth bottles, things like this. We also want to make sure we have comparative sample sets between residential sampling and municipal sampling. By municipal, I mean we're trying to grab samples that represent the distribution system, for example, from hydrants or potentially from dedicated monitoring sample taps. That's so that if we get some elevated levels from residences, we have a baseline understanding of how much lead is coming in from the municipal side. Typically, those results come back very, very low. So again, just to take away, there are different sampling protocols, and it's worth taking a look at these before we sample. One last note would be seasonally results also go up and down with temperature. Like all things, reaction rates go up with temperature. They double for every 10 degrees rise Celsius. So in the summertime, we tend to get higher lead results. So just a note of caution that the time of year can affect the sampling, even with all other things being constant. Moving on to the different ways in which we can treat lead. So if we have a community in which we have lead-bearing fixtures, we're seeing lead results come back elevated, and we want to centrally treat for that. How do we do it? There's two general ways we can do it, pH passivation and phosphates. This first one thinks about pH passivation. Now, this rather colourful looking sort of three-dimensional image, let me briefly tell you what this is, because this really encapsulates a lot of what you need to know about pH passivation. We've got pH going from left to right on our axis. It's a three-dimensional scale, so we've also got here a dissolved inorganic carbonate, which we can more or less think of as alkalinity. That's a pretty good proxy. So pH and alkalinity. And then we have the amount of lead up the side that we see. And that's what that sort of three-dimensional shape is representing. So red, amber, green. Red is where we're getting into a lot of lead. And we're trying to aim for the low points, the green points, the dark green points. And so you can see that we are generally driving for the low point of that curve, that shape, depending on what our initial water quality is. One thing to note here, there's a sort of a ridge that runs along the length of this little shape. Now, any given water quality is going to cut a profile right across that 3D image. That's kind of what you're seeing on the right there, is lead across that profile. And what you'll note, it's hard to see in both of these because it's a logarithmic scale, but the lead levels can go up with pH and they do not go uniformly down. That is to say, raising the pH and or raising the alkalinity is not a linear approach. We don't just raise pH and see lead reduction. With some waters, to raise the pH is to increase lead solubility. So it's an important distinction that it's worth looking at these types of trends and understanding what is the right pH. I'd also just note that, of course, there's often multiple compliance reasons for thinking about different pHs, different set points. It can't be governed entirely by corrosion, but the pH set point for corrosion should be thought about, and there's ways we can look at this, solubility models and so forth. On the right, I would just briefly speak to this one. This is a sort of a cut through of one particular dissolved inorganic carbonate slice out of that 3D shape you see on the left. And all you really need to take away from this, if you're interested in getting to the weeds of this, is that the two blocked shapes, that's the grey and the sort of mustard colour here, these are the two major forms of lead that we're really trying to alter the ratio of when we modify the pH. Beneath those is really a sort of a cocktail of different soluble species in lead. When lead comes into water, it doesn't just come in as pure elemental lead, it comes in as usually a carbonate or a hydroxide. And the two main ones, we've got cerussite on the left, that's the kind of grey colour, and then we've got hydrocerussite over on the right. We're generally trying to find the low point, but we're doing so by generally playing with those two species. When we change the pH, we tend to shift the relative amounts of those two types of lead. And so that's what we're doing. And these lead species coat up the inside of the pipe. They are the dominant form of metal on the inside of the pipe. And some of these species are less soluble than others. Hydrocerussite is generally less soluble than cerussite. So that's what we're trying to do when we do pH passivation. We are not trying to create a scale of calcite or hardness, carbonate. We are changing the type of mineral scale, lead scale that forms. If we have different sources are going to represent different slices across this 3D chart. So at different sources will have different set points. If we have multiple sources within a blended distribution system, then we're going to be moving around different points of this curve. So different blend ratios are going to have different lead solubilities. So I think that sort of summarizes pH. In general, we're raising the pH to get to the low point, but we do not universally get a reduction of lead by raising the pH. I'm going to talk briefly about the second method of lead reduction now, which is orthophosphate. Laith, would you mind advancing that slide? Oh, pardon me. Let me talk briefly about buffering. I forgot about this slide. One note about adjusting the pH is buffering intensity. Buffering intensity is how resilient a given water is to pH change. The amount of alkalinity in the water has a lot to do with how well buffered that water is. I wanted to mention this because particularly with this is most important for waters with lower amounts of alkalinity in the water. When we're choosing that target pH we talked about in the last slide, we're trying to keep the pH there. We don't want it to drift around, and pH can have a tendency to drift down in low buffered waters. And so I just wanted to note this thick black line represents the buffering intensity. It's sometimes a misconception that when we add a chemical that raises the pH and we add a little bit of alkalinity, we also get more buffering capacity. That's absolutely not the case. In low alkalinity waters, pH largely governs the buffering capacity, and it always has a minimum buffering intensity at pH 8.3. And so that's just a note because we need a stable pH for corrosion control to work. An unstable pH is in and of itself corrosive. So Laith, if you mind advancing to that phosphate. So another way, and a very increasingly common way because of the lower thresholds in lead for controlling lead is orthophosphate. This is a food grade phosphate that we can add to water. Again, another misconception sometimes with orthophosphate is that it's doing something akin to almost relining a pipe. It's forming some sort of insoluble barrier that serves as a boundary to diffusion. It's not doing this. When we add phosphate to the water, the phosphate actually reacts with that inner pipe wall, the lead pipe wall, and it forms a lead phosphate mineral. And lead phosphate happens to be very low solubility. It just doesn't solubilize very well into water. And so if we keep on dosing phosphate and keep a steady concentration of phosphate in the bulk water, we form this nice low solubility lead phosphate scale in our plumbing systems or lead bearing fixtures, and we just see a lot less lead come into the water. So that's enough to be said about that. Oh, one comment: polyphosphates. Polyphosphates actually react almost oppositely, and sometimes this is confusing because they're phosphates too. But when we're talking about benefiting lead corrosion control, we are talking exclusively about orthophosphate. Polyphosphates are used for sequestration, so control of usually iron and manganese, and they'll actually increase the amount of lead in water because they want to grab any divalent cation. They don't care if it's iron or manganese or lead. They will grab that, hold it in suspension in the water and through to the customer tap. So just a note to say that when we're talking about phosphates for corrosion control, lead corrosion control, we are exclusively talking about orthophosphate. A brief comment about chlorine. Does chlorine impact corrosion? The quick answer is yes. It can do so through a couple of ways. One is that it changes the oxidation reduction potential of the water. What that means in the case of lead is lead normally, if you can think all the way back to your the high school chemistry days, is a 2+ divalent cation. When the ORP gets high enough and we get oxidizing enough, and chlorine's a good strong oxidant, it can actually go up to this 4+ state. It jumps to that state. When it gets there, it forms a nice, very low solubility lead dioxide. And the reverse is true. If we have chlorine maintaining us in a really well oxidized state, and we lose that free chlorine, then we can see lead start to go up. And that was the case for Washington, D.C. when they changed from chlorine to chloramine back in 2000, had a big lead spike as a result. And so sort of finally, a little note about how we can deal with lead in a more sort of localized way. So we've talked about centralized treatment. Can homeowners help manage lead? Yes, they can. Flushing is very good advice. Flushing water, particularly prior to first use in the morning after that maximum stagnation period, really helps reduce lead exposure. It's great advice. It is not a fix. It's not a long-term solution to a lead problem. Point of use filters. These are the type of under-counter mounted filters that we could buy from a big box store. It can also be a sort of pour-through jug type. They use activated carbon. These are quite good. There are some which are certified for lead removal, and they can actually be a pretty good fix system-wide for systems that are small enough. By small enough, I define that as less than 500 residents. And also, these point-of-use activated carbon filters have been used by a lot of utilities. If they know they have lead inventory they want to remove, they've actually issued these proactively to higher risk households with young children, pending those sort of municipal upgrades. So that's so much for the homeowner. On the utility side, effectively to try and remove as much lead-bearing elements within the municipal system as possible. As simple as that. And so that rounds up my portion, and I believe we're now going to be handing over to Tom.
Kia ora all, and thank you for the opportunity to share a little bit of our experience over the last few months. Just want to touch on a couple of things first. Both Laith and Simon and Stantec generally have been really supportive in terms of partnering with the DCC and sharing their expertise. We've learnt a lot from these guys in the first few weeks of this event, and latterly as well. Lead in drinking water is a reasonably complex issue, and one that I know we weren't holding a significant level of experience on, and I believe that's probably the case for a good proportion of New Zealand. Look, I'll give you an overview of where we're at the moment, and there'll be a few things that I won't go into too much detail because we haven't yet shared that with our community, and I think it's right that we are sharing those things with our community initially, and then learning more widely across the New Zealand water sector. So we set out to look at metals in the network as an exercise in looking at corrosivity with a kind of asset management hat on. We're looking to test a couple of hypotheses. All of that seems completely and utterly inconsequential now, because what we found was quite a variable level of lead and quite a significant level of lead in the first 6 months of testing. That was kind of characterised by a really significant reading on the 8th of December at 39 times the MAV, which is a pretty terrifying number in itself. But when you paired it with all of the other results that we'd had over that 6-month period, wasn't yet that kind of major trigger for alarm. We've been testing all over our network and at our raw water reservoir as well. What became really alarming was then when all of this started to look like it was pieced together in a much wider, potentially catchment-wide or plant-wide issue. And that was a 5 times MAV reading in the raw water reservoir on the 20th of January. And that really triggered our do not drink response. It was definitely, in the eyes of public health and us, was a game changer. So at this point, we had a kind of broad level of results, varying from 39 times MAV, which was the highest by a long, long way, through to stuff that was kind of just pushing up towards the MAV on a reasonably regular basis. And we've been testing at a range of sample taps, but because this was a reasonably cheap and I guess cheerful exercise looking at corrosivity in the network, we had been testing from a couple of convenient taps at the back of a couple of local sports clubs. So one was the local golf course in Waikouaiti, and the other was a bowling green in Karatani. Those were the two that yielded the most significant results. On the 2nd of December, we issued a do not drink notice, and since then we've taken over 2,000 samples in a number of different places in an attempt to narrow down the source, and a alarming proportion of those have been non-detects since. And the reason, one of the most significant reasons for that, we believe, is we were sampling on the customer side initially with that first set of samples, and then as we moved to the network side and starting to get a representative sample from the network, we found very little, if any, lead. But obviously, We've still got other results to work through, stuff like the single result in the raw water reservoir that really gives you an indication that it would be an easy and convenient thing to explain this away with it's a customer side issue. And with those kind of raw results, you start to really have to test yourself and test the thinking to make sure that we have got this right. So we've been working through that in detail, and it's taken a lot of time. So 10 weeks later, we're feeling like we're almost there. But I guess I'd just give you a reasonable breakdown of the kind of impact on our business. So roughly 40% of our total Three Waters team resource was dedicated to response in the first week of this event. It wasn't like a boil water notice. It wasn't one of those ones where we just get to ask everyone to boil their water and hope that that's okay. We ended up having to set up dedicated drinking water stations and truck water from town, a trip of about 50 minutes. We ended up setting up something like 10 drinking water stations around the community. These were tanks that we then had to establish a monitoring regime for and all of that sort of thing. And then after that, for the next 9 weeks, we've been operating with about 10% of our team's resource dedicated to this work and dedicated to finding some answers for our community, which is, in the scheme of things, is no small effect, and has certainly been the most significant source in my kind of 3 years of leading this team, the most significant source of both acute stress in that initial first few weeks, and then latterly chronic stress. Right, it's been a long time. It's been a long time and a lot of hard yards to try and get to some answers for the community, but something that we are getting very close to an endpoint on now. Now, I guess I'll just touch on a couple of high-level things that we've found, and I guess you can draw a lot of parallels between what both Laith and Simon have said in the start of this presentation. What we've found broadly, and one thing that we thought was surprising, was we've got quite a lot of lead-bearing stainless steel in our network. So specifically in our dedicated sample taps, we've found really significant levels of lead coming out of stainless steel in different parts of the network, and also stainless steel out of valves from some of our reputable suppliers. We've also found significant levels of lead-bearing brass in our network. Stagnation tests overnight, so taking 12 hours with end caps on the end of a backflow preventer, have yielded some terrifying numbers when you compare them against the MAV. And that's all true for backflow meters for traditional manifold setups, if you're using the ones with a brass base, and then customer side tapware as well. I guess some of the lessons we've learned from this are we won't be sampling customer side as our main proxy for making decisions in the future, especially when we're looking for metals and any other contaminants. There's so much variability especially in golf clubs and bowling clubs, by the way. There's so much variability just after the supply leaves your network, and it's really hard to account for that. Variability like usage, variability like the types of fittings and other elements that are used, variability like the age of those fittings and pipes, all of those things can have a really significant impact, and minor changes in the level of corrosivity in your water can also start to create some crazy fluctuations. And I think Simon described that with a bit of an overview before, but when we talk about the significant levels of fluctuation, I guess the number that stands out is that 39 times MAV value. I would also recommend having a good hard look at brass in the network or in your networks. We certainly have, and even found that quite modern brass in New Zealand is, if you undertake a stagnation test, you'll find some quite significant results on. I think nationally, one of the learnings too is that we really need to think about clear standards for fittings and tapware, and whether or not as an initial step that's just adopting the already quite well developed North American standards, or whether or not that's something more specific for New Zealand, I'm not too sure. Certainly something we need to follow up on though. I think we also need to think about that concept of point of supply. the idea that a network utility or a water supplier's responsibility ends at the point of supply with lead is kind of inherently flawed. If you're serving up a really corrosive lead-free product, then that is going to have an impact on your consumers' public health eventually, in terms of lead and other metals, other metallic elements in the water supply. So, for instance, we found that when we test at the Waikawaiti Golf Club outside the boundary and get non-detects all day, every day, we still get really significant levels of lead on the inside of the boundary. Now, and that is even with quite, comparatively to the rest of the country, the Waikawaiti supply it's got quite a low level of corrosivity. But what we have found is that it has a reasonable degree of variability, not necessarily in the pH and alkalinity or those kind of traditional measures of corrosivity, but rather in the chloride sulfide mass ratio, which is a new thing for us, something that we hadn't considered in a bunch of detail before, and that we hadn't thought about as a kind of key risk within our drinking water network. We have a mine upstream of our water intake that does impact that chloride sulfide mass ratio by discharging sulfides from their waste rock. Typically, their discharge actually benefits the level of corrosivity in our water. However, the variability that it provides after a rainfall event, that's the real challenge for us to manage going forward. At this stage, that's all I'll share for the moment. But what you can expect is a comprehensive report for our community soon. We're working really hard to try and make sure that that report is something that not only satisfies our public health entity at the moment, but also that builds a bit of trust with our community again, because going through an exercise like this is not just acutely stressful from a drinking water supplier's perspective. It's also acutely stressful for anyone in your community, and certainly full disclosure and making a real effort to explain things in detail and make it really clear where one of these types of events has come from and how widespread it might be, and all of that sort of thing it is fundamental to building trust and making sure that we can continue to operate as a drinking water supplier that has credibility, I guess. So once again, thank you for listening, and I hope all of you who are beginning to test out there at the moment are learning quickly and hopefully not finding anything quite as acute as what we found. And if anyone wants to give me a call, you're welcome to. Cheers.
Tom, thank you very much. And I would like to just respond by saying, look, it must have been a particularly stressful couple of months for the community and for you and your team. And so thank you very much for sharing that. For anyone that joined partway through the webinar, we have been recording this, and we'll make sure that a link gets out to the attendees. So don't worry if you missed anything. But what I would just remind us all of is that the questions, please, if you could send them through in writing, type them through to the chat function, then we can work through those. We've got about 10 minutes, and we'll see how many of them we can get through. If we can't get through them all, we will endeavour to get a response out to anyone who's still looking for an answer to a question. Okay, so the first one is from Mr. Jim Graham, who will be known to many of us on the call. And the question is, and I'll ask you, Laith, to start with, if that's all right. Should a regulator be requiring a utility operator to test for heavy metals?
Okay, well, I think let me see how to answer that. Well, I was once speaking with a manager for a sulfuric acid plant, who told me that because of the extremely corrosive environment of his plant, that special pumps, pipes, and valves had to be used of the highest quality in order. But nevertheless, he still had to explain to his superiors that every time he made a shipment of sulfuric acid, he was shipping a part of his plant with it. And so these things had a definite replacement period. that may be an acceptable way to operate a sulfuric acid plant, but not, I think, a water supply. And so the only way to confirm that you're not distributing that your product delivered to the customers is adequately non-corrosive is by testing it. Now, I would hasten to add that there are different sampling protocols intended for different purposes. So there, as Simon discussed briefly, there are, and this is a large subject, but there are specific protocols that are intended to verify the performance of corrosion control programs. There are other protocols that are intended to reveal meaningful exposure, typical exposure levels. And there are other protocols dedicated to locating sources of lead, for example, in a system. So that's an important part. But to answer your question, yes, there is a duty to verify that corrosion control is adequate or that it's unnecessary. And the only way to do that is by checking.
Thanks, Laith. The next question I'd like to ask to both Simon and Laith, and that is, should New Zealand consider reviewing and reducing the MAV for lead in our drinking water standards?
Well, to anyone who is contemplating what that MAV should be, I would say two things. One is that the current MAV is not a health-based value. It is one based on pragmatism and feasibility. That's traditionally been the case. If you look back, the WHO standard in the 1950s was 100 micrograms per liter and was gradually reduced over time to 10. There's ample evidence to suggest that there is an benefit for reducing it further, and that it is feasible to do. And Health Canada in 2019 published a quite a good technical document, basically reviewing this subject, that I would encourage anyone to look at who wants to as a first place, as a sort of a literature review element. I don't know if Simon, you want to add to that.
Yeah, thanks, Laith. I've just built on what your last comment. Others have been through this, thought process, and they've documented it. The US EPA's lead and copper rule is a very large. There's a lot of literature in there. It's a simply enormous document, and it's commensurate to the task. There's a lot of data to wade through, and clearly there's. And a country as, let's say, as legalistic as the US can be, there's a lot riding on getting those regulations correct and making sure they could be properly enforced at the state level. So there's a great deal of thought has gone into that very question, and it's extensively documented. And I think going through and reviewing those who have gone before, what data they've looked at and how they've considered it is an excellent first step in starting to frame that question. Thanks,
Simon and Laith. Simon, this question came through while you were talking, so I'll ask it to you. And it's around pH variability. How much variation is acceptable?
Right, how much is too much? So the work that I usually reference on that was it was just observations through lead and copper rule. I often refer to lead and copper rule, although there's other regulatory frameworks, because they have such a large body of data to work with. They probably got the biggest body of data to work with. So the data's, so the conclusions from that data are pretty good. And their observation was that pH swings greater than 0.5, that is to say 0.25 in either direction, approximately, that's where they started to see pH in and of itself. They were concluding that's causing corrosivity, so a range of 0.5. And I would just note that's not just within where you have blended systems where the pH might swing around because you're blending in an uncontrolled way different sources with different pHs. That pH variability is also in and of itself corrosive. But the answer is 0.5. That's the sort of magic number, rule of thumb, that LCR concluded.
Thanks, Simon. I notice we've got about 4 minutes left on the call. What we plan to do is just keep going with the questions, which will probably mean we run over. If folks do have to jump off the call, as I said before, we are recording this, so you can catch the questions potentially at the end. I have another one here for you, Simon. Where is it? If we dose orthophosphates, will that create an increasing accumulation on the pipe wall that can be released quite quickly if dosing stops? In other words, once you start, do you need to keep going forever?
Yeah. So there's a couple of questions within that question. So I'll break it up into two parts. The first is, do you have physical accumulation of orthophosphate at the pipe wall? And the answer to that is no. Interesting with polyphosphates, we do see a thin film, a noticeable film form at the pipe wall, but with orthophosphate, it's really not observable, that film. We're just forming that lead phosphate mineral, and that's what's controlling things. That said, it's the right question to ask. If we lose orthophosphate, if we lose a metering pump, do we suddenly create some destabilizing environment, and is lead going to spike? Actually, I had reason to look into that question in some detail maybe a couple of years ago, and actually some of the best information I found was from my home country of Scotland. The regulators there haven't been using orthophosphate. You know, it's been in popular use since the 80s for lead corrosion control, so they've had to deal with this question. And in general, we don't see much uptick in lead during if it stops for a couple of days, 2-3 days. After that, we start to see levels rise, but they would typically rise to pre-dosing levels. They wouldn't generally spike, but the window is maybe about a week. But as to maybe it was a three-part question, because the last point being, once we start dosing, are we then committed to dosing? Until such time as that dosing is not required, in other words, lead service lines have been, not lead service lines, lead-bearing materials have been removed to the point where that's not a concern anymore. Yes, that's correct. The water has to be maintained. We have to reduce the corrosivity of the water until there's nothing left for that water to corrode.
Thanks, Simon. Question from Noel, maybe Noel Roberts. The same US lead-free municipal products are available in New Zealand but cost more. What has the overseas experience been in utilities not buying the cheapest available product?
I could probably say that that all materials in contact with potable water must be NSF 61 compliant. Whether or not they're the cheapest, I can't comment. There is a thriving market there, so there probably is a range of products that still have that certification. But I mean, the general experience, I mean, I live in Canada, where we often borrow from our southern neighbors, but the general experience of the lead and copper rule in the US over the last, since 1991, when it was promulgated, has been significant. There has been a significant reduction in lead exposure. So I don't know how else to answer the question other than that situation wouldn't occur here, because if the components don't have that NSF 61 certification, and this sometimes happens, but then there's a deviation in non-compliance, and corrective actions have to be taken to replace it. But if I understand correctly, that situation wouldn't happen here, and so it should be a requirement. I don't know in which piece of regulation in legislation in New Zealand, but basically that if materials are used in contact with potable water, then they shouldn't leach and induce toxicological effects or be composed of lead.
Thanks, Laith. Tom, question for you. You thought you got off lightly, hadn't you? Had DCC just been using LSI for determining the corrosion properties of water in the past?
Yeah, probably. Yes.
Okay.
Can I jump
Yeah.
on the back of that as well? Langella saturation index. The industry has been trying to stamp out the use of LSI for corrosivity for a long time, and it does not relate to lead corrosivity. There are sometimes coincident reasons why supplies that have a positive LSI sometimes have lower corrosivity, but I mean I've directly worked on groundwater supplies with very positive LSIs that are corrosive to lead, and that has to be resolved. So LSI is not a corrosivity indicator. Most of the regulatory documents try and put that in big bold letters wherever they can, and there was a little area that allowed for control of hardness. It was a kind of a niche thing that was in lead and copper, and they finally stamped that out as well in the latest revision. So LSI, not an indicator for corrosivity, for lead corrosivity.
Thanks, Simon. Next one I'll throw to you as well. To accurately determine if the risk of heavy metals leaching, would it not be better to test for corrosivity rather than heavy metals?
I'm trying to interpret the question. So test for corrosivity rather than heavy metals. I mean, I guess the current approach is that the presence of metals is the best direct indicator for corrosivity.
Yeah.
There's a number of ways we can quantify corrosivity. We've got pretty good, well, they have the limitations, but they're fairly sophisticated solubility models for lead, copper. We can do coupon immersion testing, taking it from the desktop to the bent scale, and we can do pipe rigs. All of those things are proxies. None of them are as good as sampling out in the field, and often there's much to be learned where we think we have good desktop bent scale. Pipe rig tends to get pretty good with that information, but the best measure is direct measurement of the metals, would be my opinion.
Mm-hmm. I could like to add to that there's a lot of there is an element of corrosion that is poorly understood that involves biological processes, and those are very difficult to study in vitro, shall I say. You know, there are processes, especially with copper and so on, where microbiological processes may dominate actually corrosion phenomena.
Thanks, Laith. So this one I'll just open up to any of the three of you. It's from Noah. Given we have very little data on what is coming out of customer taps, should we not start customer tap sampling to see if it is a broader problem?
I will say that if you do that, you have to be very careful. Something that we haven't talked about, but is widely accepted if you dig down into the weeds. But the hot water system is not considered potable, and the way most hot water systems work will result, if you measured it with elevated metals right across typically, and the way some valves work at fixtures or sinks, you have to be careful that there is, I'm speaking from experience during an investigation that we did in which we would have false positives resulting from thermostatic mixing valves that were deficient and were mixing hot water with cold water. And we verified this with just measuring the temperature. Entering the building was 10 degrees, at the tap was 20 degrees. It was clearly we ended up disassembling the unit below. So when this applies not just to lead, but any kind of sampling that occurs on the customer side, whenever possible, you want to avoid it. But in the case of lead, I think it should be done, but measures should be taken to ensure that you're not getting hot water crossing over and similar other spurious sort of phenomena.
I'm going to add a little on that, and I'm going to be very ambitious and also at the same time see if I can't take a shot at Jim's question, which reads that I talked about sampling from individual houses, but should water suppliers consider sampling from the network, which is sort of the corollary of this question of sampling from homes. I would just add, yeah, you really need to sample from private residences with respect to lead to define that problem, and that comes squarely under the issue of shared responsibility that Laith alluded to at the beginning. But also, most sort of regulated sampling programs require so many properties. There's different ways in which those properties can be prioritized, private properties, but also they generally require sample collection from, as a minimum, hydrants, better still, dedicated network monitoring taps. In order that the data from the private residences can be demonstrated to be occurring downstream of the water main. And there was another comment here that, it's maybe it relates to the same item, so you don't mind, David. I'm sort of trying to throw all these together into one item here, but that Tom had noted the challenges of sampling inside the property. So I'll let Tom maybe add any comment he'd like to on this. But what I'd say is I think Tom identified that there's challenges with sampling from properties, and that's where we can definitely see those elevated lead results. When we say problems, though, I mean that's in a sense what we're looking for. We are going to pick up more lead, copper, zinc, etc. when we're monitoring from plumbing systems. But any lead corrosion monitoring program would generally require private properties and baselining from the municipal system.
If I can just add to that, I mean, what you're trying to do is to capture a cross section of the housing stock. So as opposed to assessing exposure, if you're the water supplier, you should have a sampling program that takes housing stock from different ages, for example, pre-1975, 75 to 2000, 2000 on, and test that way. But in addition to that, and this may fall under outside of the jurisdiction of Taumata Arawai, I'm not sure, but I would say that additional sampling for exposure, not corrosion control, but exposure evaluation should take place at schools, daycares, and other facilities that serve sensitive subpopulations like that. And that's a different type of sampling.
And just to add to that further, so when I was speaking earlier around that point of supply and consideration of that point of supply, this is exactly what I was referring to. It's not as straightforward as just saying the water on our side of that point of supply is safe, so job done. And I think wrapping in customer side sampling into the whole process of managing public health and the impact of a water supply on public health, I think is absolutely something we should be thinking about. Quite how we do that and all of that sort of thing needs to be carefully thought through. So our challenge directly resulted from sampling at the most likely place to get really high lead readings, and then having to work back through our supply chain in its entirety to eliminate other things, and that's a big undertaking. So I would advocate working from the catchment through the treatment process, through the reticulation process to get your assurance right with metals, and then moving on to the customer side. Otherwise, you open a can of worms like our one.
But there's a related question here around stagnation and its water age, I guess. Do we identify areas within the network that has stagnation and only sample in those locations? Anyone want to comment on that?
Well, I mean, this goes back to why you're trying to monitor or test in the first place. If you are assessing a corrosion control program, then there will probably be, you want to capture a worst case scenario. I'll give you an example. In the city of Ottawa, there was one of the people who worked at the plant lived right next door, and they basically sealed off her system for 36 hours or something in order to be able to take a sample and obtain a worst case scenario. So that stagnation times are going to give you, and this is an actual problem in North America right now with extended shutdowns and low occupancies of buildings and such. But stagnation times are problematic, and you need to avoid them. But in terms of capturing worst case lead content and therefore efficacy of corrosion control, you should target. Stagnation times are effectively part of the sampling program. Now, if there are sections of the reticulation that experience stagnation regularly, like the part adjacent to a PRV or something, that's a separate matter. That's a condition that should be avoided to begin with for other water quality reasons, and not specifically for lead.
Thanks, Laith. One or two questions have come back around the DCC experience. So Tom, this will be the last one, I think. The question is if Tom and DCC could have done anything differently with their approach, what would it have been?
There's a whole range of things, but if you work back through the supply chain, or the cause and effect of where we ended up, I would be sampling from dedicated sampling taps much earlier, and in fact I don't think we'll start any types of metal studies in the near term that include the variability of the customer side. So just to ensure that we've got everything right on our side of the supply chain before really trying to open up that wider picture. But in saying that, there's a number of other lessons, so just had to pin down one.
Still early days for you, I'm sure, Tom. Listen, folks, I'm conscious of the time. I'd just like to take the opportunity to thank Tom, Laith, and Simon for their time. I'm sure you've all found this, really useful, and it does start that conversation that really needs to be had in New Zealand and other parts of the world, no doubt, as well. So thanks very much. I hope you all enjoyed it and found it useful. If there are further questions, by all means, send them through to me, and I can connect you with either Tom, Laith, or Simon. They really are an email or a phone call away, and are always keen to have a chat about these things. So I think that's the end. We'll, hope you all enjoy the rest of your day, and thanks for joining.